Magnetic field from a long current carrying wire. Here we have two wires. We're looking for the magnetic field at point B. Let's take a look at them one at a time. So we'll just look at that top wire, the one where the current's coming out of the page or out of the screen. And if you put your thumb in the direction of the current, then your fingers, if you're using your right hand, this is the right hand rule, if your fingers naturally curl around that wire in the counterclockwise direction. And so that's the direction of the magnetic field. The magnetic field forms concentric rings or circular paths around this wire in that direction. And that direction is determined by your right hand. You put your thumb in the direction of the current, and your fingers naturally point as they kind of wrap around the wire in the direction of the magnetic field. Of course, we draw it as a circle around the wire, but really, if you're standing, if I was standing at the origin, what direction would the magnetic field be pointing? To the right, perpendicular to this circular path that we drew. The magnetic field at the origin would be pointing in this direction. And if I was standing right here on the path, the magnetic field always points perpendicular to the path. But we draw it as a circular path. It's a little easier that way. Okay, so if I'm standing at point B, there's point B, then there's some circular path that comes around, and the magnetic field, due to I out, I'll call it B out, is pointing in that direction, sort of up and to the right. Okay, so practice the right hand rule. Remember, you have to use your right hand. I'm right-handed, so I've got my pencil in my right hand, and I'm writing away my problem, and I hate to take the time to stop and set my pencil down, but that's the way it works. You've got to do that. It's the right-hand rule. We have several right-hand rules in physics, but they're all right-hand rules. We don't have any left-hand rules. Okay, so let's figure this out now. We're going to use our equation, the magnetic field, mu naught I over 2 pi r. And that just comes from Ampere's law. You can review that. So that's around an infinite long wire, straight wire. And in this case, the r is a squared plus b squared square root. And if I plug in the numbers, I just get 5 for r. And I think I is given as 10. So my magnetic field reduces down to mu naught over pi. And that is going to give you the magnetic field in units of Tesla. All right, so if let me go back to my drawing here. I'm going to draw a line from, that's the distance that we just calculated, right? That's r. And this angle in here I'm going to call theta. And so theta is going to be equal to the inverse tangent of a over b about 36.87 degrees. And the angle that I really need is this angle over here. I'm going to call that phi. Is that phi? And that's 180 minus 90 minus theta, 53.13 degrees. Because now, if I have that angle, then I can figure out my, let me change to red, my b sub x and b sub y. So that's the angle of interest right now. Alright, so my b sub x, if you look at my drawing, is going to be b times the cosine, and b sub y is b times the sine of that angle, and this gives me 0.6 times b, and the other one is 0.8 times b, and b is just mu naught, which is our constant, over pi. And mu naught is 4 pi times 10 to the minus 7th. Tesla meters per amp. So when you plug in, if you look back at your expression up here for the magnetic field, if you plug in mu naught in terms of Tesla meters and amps, the amps cancel from the current and the meters cancel from R, and your magnetic field is in units of Tesla. So we can punch these numbers in if we wanted a numerical value. We could just leave it like this, but we can put a numerical value in here also, putting in the 4 pi times 10 to the minus 7, and I get b sub x is going to be 0.6 times 4 times 10 to the minus 7. And this one, b sub x points to the right. That would be the positive x hat direction. B sub y points up. That's the positive y direction. So they're both positive. If we're calling, I guess I should put, let me go back up to my drawing here. Oh, we already have our x direction is to the positive direction is to the right, and our positive y direction is up. That's given, I guess. The coordinate system is already given. So these are positive values. They point to the right and up. And if you look at the other wire, let's do that. Now we're down here, and this current goes in. So you stick your thumb down into the page, and your fingers sort of naturally curl around in the clockwise direction if you're using your right hand. And so we get these circular paths. That's the magnetic field. And if we're at location B, the magnetic field points in this direction. There's our radius. And so that angle is the same. Those angles are the same. That's 90 degrees there. And so we get the same results, only this time we get b sub x. This is due to I in. Let me go back up here. This is due to I out. And then, of course, we'll add them up. So we have a b sub x is b cosine phi, and b sub y is negative b sine phi, because it points downward. And the y directions cancel out. So our total magnetic field is the magnetic field from the inward current plus the magnetic field from the current coming out of the page. We do the vector addition. and the y components cancel, and we're left with 2 1.2 mu naught over pi in the x hat or I hat direction. And if you want to just have a number here, we could plug that in, what mu naught is. And these units are Tesla. Okay, so main thing here is the right-hand rule. I know we have a lot of right-hand rules, just keep them straight. This one is the thumb is in the direction of the current, and your fingers kind of curl around the wire, giving you the direction of the magnetic field, how the magnetic field encircles that wire. It forms concentric rings around that wire. And then it's superposition. You find the magnetic field from one wire, the magnetic field from the other one, and do the vector addition.